A logistics company deploys an autonomous delivery drone. It navigates a mapped grid for weeks. Then it encounters an abstract obstacle it hasn't seen before, like oddly shaped construction scaffolding, freezes in midair, and drops out of the sky. That failure usually happens because the system was poorly matched to its operating environment. Across the tech industry, organizations are burning through outsized budgets and damaging career capital by treating AI and machine learning as identical marketing buzzwords. Conflating the two leads to a specific tactical error. You end up buying an overly complex, expensive learning system to solve a simple workflow problem, or you build a rigid system that shatters the moment it enters a fluid environment. Escaping this trap requires looking past the marketing copy to understand the architectural difference between a system built on programmed rules and a system built on raw data. Knowing the difference provides the framework for a project's survival. Choosing the right architecture at the start is the deciding factor in whether a project reaches production or ends in a total loss. Artificial intelligence is the broad, overarching goal, creating machines capable of mimicking human reasoning and behavior. Machine learning is a specific method used to achieve that goal. It is a tool within the toolkit, not the toolkit itself. This Venn diagram shows the structural hierarchy. All machine learning is AI, but not all AI is machine learning. The outer AI circle uses logic or calculations to seem smart. The inner ML circle achieves intelligence by learning from vast data, instead of explicit programming. Systemic failures occur when teams treat the overarching goal and the specific statistical method as the same thing. To see how a system can be intelligent without learning, we look at the outer circle of AI, specifically the framework known as an expert system. An expert system does not need to learn from external data to function. It runs entirely on hard-coded rules, logic trees, and if-then statements explicitly written by a developer. A classic video game boss is a perfect example. When a player swings a sword, the boss reacts instantly with a perfectly timed robotic block. The boss appears intelligent and reactive, but it is doing nothing more than executing a strict set of pre-programmed rules. It never actually learns from your gameplay or changes its strategy. This rule-based approach is highly predictable. It gives you total control over the machine's output and requires zero external data to function, making it much faster to deploy. The trade-off is absolute rigidity. Because the system cannot learn, it will never adapt to an unforeseen scenario. If the player does something the developer didn't code for, the intelligence breaks. An expert system offers complete control, but it forces the creator to accurately anticipate every single possible scenario in advance. Machine learning shifts that methodology by getting computers to act without being explicitly programmed for every movement. Instead of writing thousands of strict if-then rules, the developer feeds the system millions of rows of historical logs. The algorithm analyzes that history, finds statistical patterns within the data, and essentially writes its own logic to handle future inputs. A modern email filter illustrates this pattern recognition. Sorting millions of emails manually is impossible. Instead of writing rules for every spam word, the system analyzed millions of categorized emails, learning to detect junk autonomously by identifying recurring linguistic markers. This yields an adaptable system that improves over time, but it demands heavy upfront processing and significant computational resources. You trade away line-by-line developer control to gain the ability to evolve. However, without a deep reservoir of clean data, the system remains completely useless. Placing these two paradigms side by side reveals how they impact your resource allocation. This matrix shows the primary mechanisms. On the left, we have rule-based AI, executing logic. On the right, we have machine learning, processing data. Looking at resources, the left side requires human domain expertise to manually write the logic. The right side requires high-end server capacity and extensive historical datasets to train the algorithm. For adaptability, the left side remains static, while the right side displays an upward trend, predicting new outcomes based on its ongoing experience. To see the difference in autonomy, look at this robotic chef. The robot on the left operates on an expert system. It knows what to do because it is following a recipe card. The robot on the right uses machine learning. It tastes 10,000 different soups to deduce the perfect ratio of salt on its own. The architectural choice dictates resource allocation. You must decide whether to pay for a programmer's time to write rules or for a data server's processing power to find patterns. Moving toward practical application means knowing how to choose the right architecture for a specific problem. This flowchart begins with a gating question. Is your problem environment 100% predictable? If the answer is yes, you route to an expert system. Highly regulated environments, like basic customer service routing or strict financial compliance checks, work best on clear, predefined rules. If your environment is chaotic, you follow the no branch to a second question. Do you have a high-volume archive of historical data? Having the data unlocks the machine learning path. Lacking that data in a chaotic environment requires stopping to reevaluate your infrastructure. Deploying machine learning on a chaotic problem without the necessary historical data leads to project failure. The nature of the problem space must dictate the architecture, not a desire to use the trendiest technology available. For those managing static, highly structured workflows, expert systems are often the more efficient, faster, and more controlled route. Developers tackling chaotic problems like fraud detection or user behavior must accept the substantial overhead required for machine learning. Those fluid environments offer no other choice. Chaotic spaces require systems capable of changing their own shape. Rigid rules cannot keep up with mutating threats or shifting variables. The primary risk is building a system based on how smart the label sounds to a board of directors. The real tension exists between using programmed rules or relying on data-driven experience. Getting a project to production requires cutting through the marketing hype and matching the mechanism, rules or data, to the specific demands of the problem.